Welcome. In this video we continue our development of the direct stiffness method as applied to truss and beam structures. So in a previous video or in other videos we looked at how the stiffness, the direct stiffness method is the method of choice in order to assemble the stiffness equations of a system such as this truss. And details are seen in other videos, but to recap the important parts for this video, we have the system composed of 5 nodes and some trusses. And the stiffness assembly involves generating the matrix system of equations that describes the system. So the process basically involves iterating over each element E. So for each element E, we get the stiffness matrix of that element, and those stiffness matrix is a part that it's a matrix that is related to only the degrees of freedoms which this element connects, as well as the right hand side vector. And using the map or the degree of freedom map from local degrees of freedoms to global degrees of freedom, we can add the contribution of this element into global stiffness equations, and that's the pseudo Python code used for that. And you can see that using the DOF map, I can map ij components of the element stiffness matrix directly into PQ components using the global degree of freedom numbering. Now, critical in this step is that we have the element stiffness matrix and the element equivalent nodal forces. Now, other than that, the direct stiffness method, as it is written in this slide, applies to any system that you can think of that can be written in terms of a stiffness equation. So basically all linear partial differential equations. In this case, we're going to specialize this for the truss element. And just a word of caution, this video is a bit heavier on the math as opposed to other videos. So I would suggest stopping and pausing the video frequently, taking notes. I strongly recommend taking notes for this one so you can follow the math, okay? So we start just by remembering what each of the components are. We have the element stiffness matrix, we have the elements degrees of freedom in global coordinates. These are the subset of all the global degrees of freedom that belong to this element, as well as the equivalent element nodal forces. Okay, so if the element has some body forces or other forces that are applied directly to it and are part of the element, those go here. Okay. Now we start with a 2D truss element in its original configuration. This truss element connects nodes Ni and Nj of the global structure. Ni is located at coordinates xi, y sub I, and Nj at xj, y sub j. From that information, we can compute the original size by just taking the subtraction of all coordinates, squaring those, and taking the square root of that. So this original length is just the norm of that vector. In addition to that, we have a cross-section area for the element. We have a modulus of elasticity. We're assuming just linear elasticity and some density rho. And we define horizontal and vertical degrees of freedom at each of the connected nodes. In this case, we're going to call U0, U1, U2, and U3. And the superscript E denotes that this belongs to element E. Now, the displaced configuration is the final position of the truss bar once equilibrium in the global structure has been reached. So we can think that this, the position of those nodes after they have been displaced is just adding the corresponding degree of freedom. U0 in this case adds to the x component of the I node and such. So from this we can find out what the final length is, so the deformed length of the truss element. And it's using the same equation, so wherever we have x, we just add the corresponding degree of freedom that we had from before. Okay, so here we have the addition of xj, so xj here plus u2. U2 is the horizontal degree of freedom at node j, at node 2, right? And then minus the final position of this node, which is similar. Square root, add, take square, and all of that. Take square the final positions add them and take square root. That's the final length of the element. So from this, we have the original length, right? We have the nodal positions. That original length, if I take the bar and just place it, rotate it, and place it right next to the bar with the original length, I can figure out what the increase in length, or the difference between the final length and the original length is. That's how much the bar was stretched or compressed in the process of finding equilibrium position, right? So from that, we can work out that difference, LF minus L naught, right? That's the original length. And then we have the final length, where we have added the degrees of freedom. And if we collect the element degrees of freedoms into a column vector, then the final length becomes a function of this vector of element degrees of freedom. And here's the key part. So we're going to be doing linear finite elements, and in this case we need to linearize this equation, because the final length is a nonlinear function of the element degrees of freedom. So in this case, in order to linearize, we're just going to take a Taylor expansion about this element about the undeformed configuration. You can pause this video to think about it a little bit, but this Taylor series expansion is just the undeformed length plus derivatives of the length with respect to each degree of freedom independently times the degree of freedom. And note that final length evaluated at u equals 0 is the undeformed length, and the final one is going to be the undeformed length plus the delta, so L naught plus UE is the final length. So in that way, we can approximate the final length as the increment in length plus this function evaluated at 0. With all of this in mind, we can just simply cancel this term and this term on each side of this approximation equation, and we can approximate the delta as all the part of the equation that involves the derivatives. So moving onwards, we have approximated the change in length of the bar using just the partial derivatives of the length function with respect to the vector of degrees of freedoms multiplied by the vector of degrees of freedom. And this is valid for a first order Taylor approximation, that is small displacements. Now how small is something you have to figure out for each models, but we're talking small displacements, like a structure should stay still, right? So this is in general for structural engineering, this is a valid assumption. Now, we've got this approximation for the change in length of the bar. And let's figure out a few of these partial derivatives. It actually turns out, if you inspect, for example, the first one is the derivative of this thing with respect to this degree of freedom, u2i, so that's the first degree of freedom at the I node. And if you follow through with the partial derivatives, you'll find out that you get this expression, which involves just the nodal coordinates and the changes in the degrees of freedom, over 2i's the original length, or the final deformed length of the bar. But we need to evaluate this derivative with respect to the undeformed shape. So this actually becomes the original length. And we get the subtraction of the x coordinates of the bar over the original length. And geometrically, if we subtract the x coordinates and we divide it by L2, that's exactly the cosine of the original angle that the bar makes with respect to the horizontal. So we can replace all of this with minus cosine the angle that the bar makes with the horizontal angle, with the horizontal bar. Sorry, with the horizontal axis. Okay, so for the other components, the story is pretty similar. Each of the components, we get cosine, minus sine, cosine, and sine. So at the end of the day, after all this derivation, we get that we can approximate the change of length in the bar with basically minus cosine theta of the bar, minus sine, cosine, and sine, all of that collected into a horizontal vector, dot product or internal matrix product, right, with degrees of freedom of the bar. So basically the displacement vector of the bar times this little vector here, which all it does is project the displacement vector in the direction of the bar. Now with the stretch of the bar, with the delta, we can find out what the equilibrium is of the element, or we can speak about the equilibrium. So we have the displaced configuration at the equilibrium. There's some values for these degrees of freedom, and we have a stretch vector. So for equilibrium, it is the most powerful approach for equilibrium is the principle of virtual work. And that states that at equilibrium, if the system undergoes any change in configuration, a virtual change, then if the system is in equilibrium, then the virtual work of internal forces is going to be equal to the virtual work of external forces. And this is another way of stating that the system is in equilibrium, and it's a very powerful way to do so. So the force, the axial force that's resisted by this truss member is basically the stiffness of the member, AE over L naught, times its stretch. So these S supra E, these denote basically the traction force that is resisted by the vector. This is going to be a traction force when delta is positive. It's going to be a compression if it's negative. So that's all good. And then we can also have an external force, which in this case we're going to consider it to be the weight of the element. So it's whatever the density of the truss is, times the cross-section area, times the original length. That gives you the total weight of the element. Okay, so at equilibrium, we'll have that if we displace this element from its deformed configuration by a delta, by a virtual displacement, we'll have that the internal forces are going to do a work which is exactly equal to the one done by the external forces. So this is the idea. The brown bar at the back there is the element at its equilibrium condition. And now we do a virtual arbitrary displacement of this bar. So that means just incrementing, nudging the values of the degrees of freedom a little bit in an arbitrary way. And arbitrary means whichever way you want, by whatever amount you want. No matter what the values of these deltas are, this equation right up here should hold. So we're going to compute those terms. On the other side, we have the internal forces. Those are going to undergo a change or a work that's going to be done through this increment in the element stretch, as well as the weight is going to do work because the center of gravity of this bar is going to move a little bit when it undergoes virtual displacement. So developing these equations a little bit, I'm sorry these slides are not animated at this moment, but we can start up here. The internal forces, the work of the internal forces is the stretch or the increment in the displacement or in the stretching of the element. So this delta, so it's a virtual stretching on top of the original stretching that we're applying for the principle of virtual work. And we multiply that by the equilibrium forces of the element. So we plug that into the equation. We compute what this delta is using the equation we saw from before. We call this matrix over here, we're going to call it T for a transformation matrix of the theta angle of the bar. And this here is just going to be the same delta, except for the real stretch of the bar, we use the real values or the solution values of the nodal degrees of freedom. For the virtual one, we replace the u here with the virtual displacement of the nodes. So going back, we're talking about, in one case we use these, and in the other case we use these over here, the virtual ones. Okay, so the work of the internal forces is going to be the stretch multiplied by the real member force. We work that a little bit, and we're going to get the internal force is going to be this value over here. And you can work it out to be, you can see that this ends up being this product of these T transpose times T and multiplied by that AE over L. This is going to be a matrix. and it's going to end up being our stiffness matrix. On the other side, when the element gets stretched, the position of the weight changes slightly virtually. So if we track the work done by the weight when that change happens, this is what we do here. So basically, the final position of the weight is going to be the average of the changes in the vertical degrees of freedom, right? And then that you multiply by the weight, and that's a negative work because assuming that these U1 and U3 are positive vertically and that the weight acts in the negative y direction, then the work of the weight is going to be negative. So you end up with an expression for the external work which looks like this. And if you make the internal work to be equal to the external work, you end up with these equations, right? So that's the expression for the internal work. This is the expression for the external work. You make those to be the same. And in the end, you can get rid of this. So this is a vector equality, right? So matrix times vector is a vector, and then this vector times this one transposed gives you a scalar. This is a transposed vector, so all of this is a vector, and this is another transposed scalar. And it's not straightforward that you can get rid of these, but you have to remember that these virtual displacements are arbitrary. So you can select, for example, 1, 0, 0, 0 to be your virtual displacement, and this equation has to hold. That'll give you the first equation of the stiffness matrix, or the system of equations. Or you can make it to be 0, 1, 0, 0. You get the idea. It can be whatever you want. But in the end, that arbitrariness, or the fact that the delta u's are arbitrary, is what allows you to cancel these at each side of the equation, as if it was a scalar algebraic equation. At the end of the day, you get the stiffness of the element times the displacements of the element is going to be equal to the right-hand side, or the equivalent nodal forces. And those equivalent nodal forces are given by that expression right there. And that concludes the stiffness derivation for the truss element, as well as the right-hand side. I strongly suggest, again, that you review and you work out these equations by yourself carefully, taking all the necessary in-between steps so that you can get a good grasp of the techniques involved, because this really forms the basis of what an engineer should be able to do: derive equations from basic principles. The basic principle here is the equation of equilibrium. Internal work, virtual work, is equal to external virtual work at equilibrium, and you just plug in everything. You work out what these means in each specific case, and you come up with general equations that are good for different cases. Thank you.